Can you please confirm that you can see the presentation?
Yes, sir.
Okay, thank you. Okay, so I hope all of you are able to see the presentation, and at the same time are also able to hear me quite clearly. So I shall return to what we were discussing in the last class. We finished discussing some very basic applications of Poisson's equation in the three coordinate systems of our interest, namely the Cartesian system, then the cylindrical system, and then the third, the spherical system. But in each of these, we only chose to work with one coordinate. In the Cartesian system, we worked with the z coordinate. But if we were to have worked with the x and y coordinates, it would have amounted to the same thing. Of course, in all of these equations, we are looking at the variation of the potential function with respect to only one variable. In the cylindrical coordinate system, that variable happened to be the s variable. And similarly, in the spherical system of coordinates, that variable was the radial variable r. Okay. Then we began the discussion of Laplace's equation. In Laplace's equation, once again, we began our discussion with the Cartesian coordinate system, and we took just the z variable on which the potential function depended. And but this was a case where we applied the boundary conditions. Some of your numerical problems, which will come in due course, will involve using boundary conditions to find solutions. So please try to understand the principle of how you apply boundary conditions. Let me just briefly revise some of these ideas once again, because today we shall begin more complicated discussions involving the cylindrical and spherical symmetries. So V is a function of Z. In the most general sense, by the way, V can depend on X, Y, and Z, but that requires a whole lot of complicated mathematics, which are not really a part of your syllabus. Also, if you work with the one variable dependence, you will at least get a clear understanding of the basic principle of solving Laplace's equation. So here it is that you have chosen only dependence on z. It could have been x or y, doesn't matter, but only one variable. So here we have just chosen z. And then, so the basic algorithmic flow of solving these equations is the following. First, you write the general equation, del squared v is equal to 0. Then, as per the requirement of the problem that you are solving, that is, v depends only on z, you recast del squared v equal to 0 to d2v, dz squared is equal to 0, which is the equation of a straight line. As you will notice, there is the first integral. So step number 1, step number 2, the first integral is step number 3, which is dv dz is a constant, capital A. Step number 4 is the second integral. V is az plus b. As you can see, this is in the form of the equation of a straight line. Y is equal to mx plus c. Then you apply, so that's up to step number 4. Then the important thing is to apply step number 5, which is the boundary conditions, which something that we did not do while working with Poisson's equation, because the algebra would have been complicated. Anyway, this is for you to understand the basic physical principles. So with the application of the boundary condition, one constant vanishes, b is equal to 0, and the second constant becomes v naught by h. So this is step number 5, application of the boundary conditions. And then step number 6 is to write the electric field as the negative gradient of the potential function, which is what you have over here. And the negative gradient of the potential function for this particular problem is actually minus dv dz z cap, so whose value you know already. Dv dz is a, which is equal to v naught by h. So what you have done in plane symmetry could also be replicated, sorry, what you've done for the z variable, if you had been given the same problem in terms of either the x or the y variable, but not the other two variables. So you just have, let's say, d2v dx squared is equal to 0, or d2v dy squared is equal to 0. Whatever, you just follow the same principle as we have discussed here, except that you will substitute the letter z with either x or y as per your problem. So, as you have noticed, that what we have worked with is basically the equation of a straight line when we are dealing with the one-dimensional case. Okay. So that has got certain implications. Like I said, I mean, the general solution of Laplace's equation, v depending on x, y, z, all three variables, is a formidable mathematical challenge. Not formidable, but a considerable mathematical challenge. So we don't want to get into a long drawn-out mathematical discussion. If we can avoid complicated math, but at the same time gain physical insight, that should be a more rewarding approach. So just please give me a minute. Yes, okay, sorry. So I hope all of you are able to hear me. So first we shall discuss certain, with the help of our simple one-dimensional case, v as depending on a variable, x as we have written over here, v as a function of x is equal to ax plus b, which is the same thing as what we have got here. V is equal to az plus b. So instead of z, we are just writing x. That is all there is to it. So one-dimensional case, vx is equal to ax plus b. What is an equation like, geometrically speaking? The equation of a line, the equation of a straight line like, geometrically speaking, it does not turn or twist. For instance, if you are looking at a function that twists or turns, let's say the sine function goes up, comes down, then turns up again, goes up, again comes down. So it has got an infinite number of maxima and infinite number of minima. Or if you look at a parabola, y is equal to x squared. A parabola, this will be like it has got one minimum. Or if you look at a parabola whose equation is y is equal to minus x squared. So this parabola has a single maximum. So whatever it is, these functions have either a maximum or a minimum, or sometimes multiple maximum or minimum. So these functions twist or turn. But a straight line does not behave like that. Like if you have this equation here, Vx is the equation of a line, and Vx is the average value of Vx plus a and Vx minus a. What do I mean by that? Consider this one thing, a straight line that is passing through the origin. Y is equal to x, a very simple example of a straight line. Or y is equal to x, so v is equal to x, if you want that way. So when x is equal to 0, v is equal to 0. When x is equal to 2, v is equal to 2. So when x is equal to 1, v is also equal to 1. So let us say your a, your x is like at x equal to 1. And a is equal to 1. So it will be 1 plus 1 and 1 minus 1, as in this example. So v at 2 and v at 0. So when you have that sort of a situation, v at 1 will be the average of v at 2 and v at 0. That is the property of a straight line. You cannot do such a thing for a function that has a twist or turn. Consider a simple thing. Consider the sine function, let us say. When you have x equal to sine x, if I were to ask you to work with sine x. So when x is equal to 0, sine x will be equal to 0. When x is equal to pi by 2, sine of pi by 2 will be equal to 1. When x is equal to minus pi by 2, sine of minus pi by 2 will also be equal to, I think it, no, sorry, I'm sorry, I'm sorry. No, let's not talk about the sine function. Let's talk about the parabolic function. Y is equal to x squared. Yeah, that will be a better function to work with. Y is equal to x squared. Follow the discussion a little carefully. When x is equal to 1, y will be equal to 1. When x is equal to 0, y will be equal to 0. When x is equal to minus 1, y will also be equal to 1. So now you follow carefully. The function, the parabolic function, turns at x is equal to 0. So the value of the function at x equal to 1 and the value of the function at x equal to minus 1 will not give an average that will be the value of the function at x equal to 0. Will not give you an average that will be the value of the function at x equal to 0. It's like a bowl. A parabola will be like a bowl. So that is the whole point. Here in this case, though, a straight line has this property that if you take any 2 points on a straight line, then a point that is midway between the 2 points you have chosen will give the average value of the function at the 2 extremity points you have chosen. That is the property of a straight line. And in one dimension, Laplace's equation follows this property. Okay, this is a property that we shall use later in certain respects, not now. Now there is another feature of the equation of a straight line. A straight line has no maximum or minimum. A straight line is featureless, like you don't go up or come down, as in the case of, let us say, a sinusoidal function. You're going up, then you're coming down, like that you're doing all the time. But no, sir, no such thing happens in the case of straight line. What is the property of turning points? Let us now try to understand. Mathematical property. If you have a turning point, at the turning point, the first derivative of the function must be equal to 0. And if that turning point is a minimum, which is to say it is a stable turning point, then the second derivative of that, the second derivative of the function at that turning point will be positive. If on the other hand, if the turning point is a maximum, which is unstable, there the second derivative will be negative. I hope you have followed the discussion I have just stated. At both kinds of turning point, maximum or minimum, the first derivative is equal to 0. So then how do you distinguish a maximum from a minimum? Mathematically speaking, the distinguishing feature of the two turning points is that if it's a stable turning point, such as in a minimum, the second derivative will be positive. If it is an unstable turning point, such as in a maximum, the second derivative will be negative. Now you look at the equation of a straight line. The equation of a straight line always gives a 0 second derivative. Second derivative is 0, which means that it has got, if it had been a maximum, then it would have had a negative second derivative. If it had a minimum, then the second derivative would have been positive. But the second derivative all the time in the case of a straight line all the time is 0. Therefore, it has got neither a maximum nor a minimum. It just keeps on growing monotonically forever, doesn't stop. So that is the feature of, I shouldn't say monotonically. By monotonically, it means that it doesn't, I mean, it keeps growing, doesn't twist or turn, but a straight line is particularly special in the sense that, for instance, y is equal to e raised to x. That is not the equation of a straight line. That's the equation of an exponential growth, exponential function. There also the growth is monotonic. Y is equal to e raised to x does not have any turning point. But the second derivative of y is equal to e raised to x is not 0. It's only for the equation of a straight line. You can just test it for yourselves. Y is equal to e raised to x. What's the first derivative? E raised to x. What's the second derivative? E raised to x again. And the second derivative is always positive. as you can see, for both positive as well as negative values of x. E raised to x, regardless of the sign of x, e raised to x will always be a positive quantity. So there you have a positive a positive second derivative all the time, but no turning point. But in the case of a straight line, is got a zero turning point. Now I'm saying extend these principles into higher dimensional problems. What do I mean by that? In 2-dimension, least surface area is given. Let us try to understand the meaning of this thing geometrically. So I have given you a function v with respect to x. Fine, that is all right. And you are going from one point to another, following the path of that function. If that in 1-dimension, if you were to follow a geometrical configuration that obeys Laplace's equation, then from one point to another, you must be traveling along a straight line. We have been given 2 points. We are looking at Laplace's equation in 1-dimension. In 1-dimension, let us say along the coordinate axis, horizontal coordinate axis x, you just have 2 points. And I'm saying go from point A to point B. How will you go? You will ask me, how will I go? I will say you follow Laplace's equation, the solution of Laplace's equation to go from point A to point B. And how will you therefore go from point A to point B? Simple thing. Well, don't be too confused about this AB. These AB are constants. When I say first point and second, point 1 to point 2. Let me put it that way. You're going from point 1 to point 2, and you have been instructed in 1-dimension that you follow a path set for you by the solution of Laplace's equation. How will you go? Straight line. And what is a straight line between 2 points? What does it represent? It is the shortest geometrical path between 2 points. You're not twisting or turning, you're not going up and then coming down. That will be along a curve. Laplace's equation in 1-dimension gives you the shortest path. Follow my use of the word path. Be attentive on my use of the word path. Follows the shortest path between any 2 given points. And in 1-dimension, the shortest path always coincides with that of a straight line in 1-dimension. Okay. What about 2 dimensions? Instead of v depending on x, suppose I have given you a situation whereby v depends on x and y. Okay, so what will you do? Let me just go back to the geometry. So suppose along the vertical axis, you are plotting v instead of z, and you know that v depends on x and y. I hope you recall a tutorial problem. I think it was in the first or the second tutorial we worked on this problem where you were given a function, a hill function, h depending on x and y. I think it was in tutorial 1. H depending, so you plot h along the vertical axis and x and y along the 2 horizontal directions, mutually perpendicular horizontal directions. So it's like that. Now, let us see. This is the geometrical intuition I want you to gather from this discussion. Although we have just worked with the 1-dimensional problem, but this discussion will carry on to higher dimensions. What is the geometrical intuition you should gather? That just as between any 2 points, the shortest path, a path is a 1-dimensional geometrical structure. The shortest path is the equation of is a straight line. You don't twist or turn. Just follow as the crow flies. Similarly, on a surface in 2-dimension, on a surface, if you look for the solution of Laplace's equation in 2-dimension, the nature, the surface that will be the solution of Laplace's equation will have the least surface area. I hope you are able to make that geometrical connection. In 1-dimension, least path length. In 2-dimension, x and y, that is. In 2-dimension, you are no longer talking about path. Path is a line, as in your line element dl. But now in two dimension, you shall have to think in terms of a surface. You solve Laplace's equation, and the Laplace's equation will solve to give you the least surface area. Just as in 1D, you get the least path length, in 2D, you will get the least surface area. Now, what should that surface be like? Just like in one dimension, you have a straight line. That is to say, you don't have any twisting or turning. You don't have a maximum where you go up and then you roll down down the slope, and then you may have a minimum where you go into a valley, just as you don't have anything like that. So it is that in two dimensions, when you solve Laplace's equation, the surface that you will get by solving Laplace's equation, I'm just asking you to make the geometrical connection, because whatever you get in one dimension should also carry over to two dimension, geometrically speaking. The surface that you will get will have no pockets or mountain or anything like that. What do you mean by pocket? Consider, let's say, I don't know if you have played billiards or anything. I have not, by the way. So there you have holes at the corner of the table. So if a ball goes into that hole, it's a stable configuration. It falls into the hole and doesn't come out of itself. So you will have to supply energy for it to come out, meaning that you will have to work, put your fingers in and pull it out. So that's how you do it. Or let's say you have, you have a surface where there is a slight mound or anything, then things will roll away from that. So basically, when you have a mound or a little hole, a pocket or anything like that on a two-dimensional surface, those are the points where you will have vanishing first derivatives. And so like in your hill problem, you had a peak where the first derivatives, by writing gradient of this thing is equal to 0. You wrote that there was you saw that there was a vanishing first derivative over there. So you will have vanishing first derivative. But if you make the equivalence with the equation of a straight line doesn't have a vanishing first derivative in the most general sense. It's got a constant first derivative all the time. As it here, dv dz is equal to a constant. The constant a may be 0. In that case, you'll just have a trivial solution. Incidentally, I would like you to make a note of something. There is always, in all of these problems, a solution known as a trivial solution. What is a trivial solution? Trivial, trivial solution. Del 2v is equal to 0. One solution that will always work with this equation is v is equal to 0. V is equal to 0. If v is equal to 0, del to v will obviously be equal to 0. So there is no challenge. Also, v is equal to a constant. A non-zero constant is also. But a trivial solution is not something that we are looking at. We want to look for a more meaningful solution. So A will in general be a A will in general be a non-zero constant if you want to avoid a trivial solution. And so your first derivative will continue. The first derivative in your two dimension will also continue to be equal to 0. So that is the meaning that has been understood, that in two dimensions, just like in one dimension, your straight line, the solution of Laplace's equation is like a straight line. In two dimensions, the solution of Laplace's equation is like a surface with the least surface area, and the surface doesn't have any hill or valley or trough or crest, nothing of the sort. So if you were to roll down a marble on a surface which is the solution of Laplace's equation, it will not fall into a pocket or a trough and settle down over there, because there is none. So it will just keep rolling down from one boundary to another boundary. From the first boundary, wherever you have started rolling it down, to the second boundary where you end your study or your analysis. So that is the feature of Laplace's equation. Now you can also, just like we have discussed it for 2 dimensions, you can also discuss it for 3 dimensions. but then 3 dimension is not something that you are designed to understand, meaning that you will have to draw x, y, z, and then v as a function of x, y, z will be along the fourth axis. So I mean, nature has not designed us to think in terms of 4 axes, so I will not talk about that. However, be it understood that this geometrical principle will continue to hold over there. Probably it will mean that in 3 dimension, the solution of Laplace's equation would probably be like least volume kind of a configuration, whatever. Just like in 1D, it has got the least path. In 2D, it has got the least surface area. In 3D, which I wouldn't expect you to be able to imagine, it'll have the least volume, probably. Okay, anyway. So we shall use these properties of Laplace's equation later. For the time being, with the understanding of Laplace's equation that we have gathered by solving the simple one-dimensional problem in the Cartesian coordinate system, we now move on to the case of cylindrical coordinates, Laplace's equation in cylindrical coordinates. There are 3 coordinates to be worked on, s, phi, and z. We shall work with each of these variables, starting with the z variable. In the Cartesian coordinate system, I just worked with the z variable because the x and y variable problems will just be a replica of what we did with the z variable. So you just substitute z with x or z with y. But that kind of simplicity does not hold in either the cylindrical or the spherical coordinate systems. Let us see how. So variation along, sorry, just a minute, please. Just a minute. Thank you. Okay, so variation along the z direction. Neglect fringe effect. Let us have a little discussion of this word fringe effect. What do I mean by the fringe effect? You have a cylinder. Electric field lines are passing through this cylinder. So they are like straight lines within this cylinder. As soon as the end of the cylinder is reached, the field lines would spill over in all directions instead of remaining parallel to one another. So this cylinder is like a covering sheath, a coat, which is holding all the field lines within the cylinder to be straight and parallel to one another. As soon as the cylinder ends, immediately the field lines will spill over in all directions. So that is what I mean by fringe effect. The way to neglect fringe effect is to idealize the problem by saying that the cylinder is infinite in extent. So on a finite distance length scale, there is no fringe effect problem. But well, that's an idealization. We'll just say that we have got a long enough cylinder so that the fringe effect is not something we need to worry about. So here we have a cylinder. Electric field lines are passing through this cylinder, going from bottom to top, straight up or down. I don't know, whatever it is, but they are varying along the z direction. This is a cylinder. So first we shall talk about the dependence on the z-axis, which will be the same as in the Cartesian coordinate system, because the z-coordinate in the cylindrical coordinate system and the Cartesian coordinate system are the same. So there is no difference between the two. So we'll just write once again step by step. Like I said, del to v is equal to 0. As per our problem, which says that v depends only on z, we write d to v dz squared is equal to 0. Written in full glory, Laplace's equation should have been del to v del x squared plus del to v del y squared plus del to v del z squared is equal to 0. These are the two boundary conditions. Z is equal to, at z equal to 0, v is equal to 0, at z equal to h, v is equal to v naught, which is, once again, if you go back to the old problem, it's the same thing. Z equal to 0, v is equal to 0, z equal to h, v is equal to v naught. What is the only difference? That instead of a circular top disk and a circular bottom disk, you're looking at a rectangular top plane and a rectangular bottom plane. This is the only difference between the two cases. In the Z in the Cartesian system is going to follow this kind of a geometrical configuration, whereas Z in the cylindrical system will follow this kind of a disk-like geometrical configuration at the two boundaries. That is all there is to it. Otherwise, they are the same thing again. So as you can see, I've written over here, it's identical to the Cartesian case. V is equal to AZ plus B. E is equal to minus dV dz, which is minus AZ cap. Use the boundary conditions. V is equal to 0 at Z is equal to 0. V is equal to V naught at Z is equal to H to get B equal to 0. Everything is just like what we did in the Cartesian Z problem. When Z is equal to 0 and V is equal to 0, 0 will be equal to A into 0 plus B. Therefore, B is equal to 0. And then you're left with V is equal to AZ. So V naught is equal to A into H. Therefore, A is equal to V naught by H, like the 1D case along the Z direction. So here you have this thing, S phi Z system. We have solved for the Z coordinate first. It's a very simple coordinate to work with, identical to the Cartesian coordinate system. I would like you to make a note of something as we go along. In the Cartesian system, there are three variables to work with, X, Y, and Z. We worked with Z, but we also assured ourselves that whatever happens in the X and the Y directions individually should be like what we have got in the case of Z, the Z equation, the Z solution of the Z dependent equation. Therefore, in all X, Y, Z three directions, the solution of Laplace's equation will be the equation of a straight line. Here, in cylindrical coordinates, the first thing that we have seen is that, just like as in the Cartesian coordinate system, the solution of Laplace's equation along the Z direction is also the equation of a straight line. Okay. Next is variation along phi. This is also a relatively simple thing to work with. Let us see how we get this thing. No S or Z dependence. Phi, V just depends on phi. V is a function of phi, as has been written over here. Let's see. Here you have the Z-axis, here you have the Y-axis, and here you have the X-axis. That is the diagram. Phi is an angle made by the radial vector, radial vector of the equatorial plane, S, with respect to the X-axis, phi. This is just a cylindrical coordinate system. What we shall do, now we look at something important. This is the Laplacian operator in 3-dimension written in full. You have the S variation, you have the phi variation, and you have the Z variation. The S variation is 1 upon S, del del S of S, del V del S. The phi variation is 1 by S squared, del to V, del phi squared, and the Z variation is del to V, del Z squared. Your problem is saying that V depends only on phi. If that is so, then del V del S will be equal to 0. The first thing will go away. Similarly, del 2V del Z squared will also be equal to 0. This will also go away. And you are left with, therefore, 1 upon S squared is equal to d2V d phi squared is equal to 0. Why d? Because now it's just a one variable problem. If it is a one variable problem, then it's just a simple full derivative that you write. d2V d phi squared is equal to 0. No challenge at all thereafter. This is the phi variation that you're working with. d2V d phi squared is equal to 1 by S squared into this thing is equal to 0. You multiply this equation throughout by S squared, and you will just get d2V d phi squared is equal to 0. And so 1 by S squared is not 0 in general, unless of course S goes to infinity, but that's not what we are looking at. So this thing will be non-zero. So this thing into this is equal to 0. If 1 by S squared is non-zero, then d2V d phi squared is 0. Simple thing. And if d2V d phi squared is equal to 0, then that's again the equation of a straight line whose solution is V is equal to A phi plus B. Okay, so here you have the two boundary conditions. At phi equal to 0, which is to say that you're on the x-axis, at phi is equal to 0, V is equal to 0. At phi at certain value alpha. Phi is equal to alpha, V is equal to V naught. Okay. Therefore, when phi is equal to 0 and V is equal to 0, put that in this equation. 0 is equal to A into 0 plus B. Therefore, B is equal to 0. Fine. That goes away. Those are the boundary conditions we are applying. We did not apply boundary conditions in the Poisson problem. Remember that. But we are doing it in the Laplace problems because it's so much simpler. Ultimately, basically, in Laplace's equation, you'll see an overwhelming number of cases will be the solution of the equation of the straight line. So it's a very simple thing to work with. That's why we can easily apply boundary conditions and try to get. It doesn't mean that in Poisson problems, the boundary conditions should not be applied. They should be, except that it'll take the rest of the semester for us to work out a few of the mathematical problems if you want to do all the things in their with their proper mathematical rigor. That is the thing. Okay, so when B is gone. When phi is equal to alpha, V is equal to V naught. Therefore, A is equal to V naught by alpha. V is simply equal to V naught into phi by alpha. So that is the equation that you get for the variable phi when there is no dependence either on S or Z at the same time. Now, you will have to apply the, to find the electric field. And what is the electric field? Gradient of V is dV ds s cap plus 1 by s dV d phi phi cap plus del V del phi phi cap plus del V del Z Z cap. So V does not depend on Z, this vanishes. V does not depend on S, this also vanishes. You're just left with this thing, a full derivative, and that will be negative gradient of a scalar function. Negative gradient. Electric field is just that, negative gradient. This thing is the only thing surviving of the scalar function. So 1 by S d V d phi phi cap, that is what you have. And what is dV d phi? dV d phi will be equal to V naught by alpha. You take the derivative of this equation, dV d phi, V naught by alpha, so minus 1 by S, V naught by alpha phi cap. That is the solution of Laplace's equation, how you find the potential and the electric field in terms of the phi coordinate. That is how you do it. So this Laplace operator and this gradient operator for curvilinear coordinates, S phi z or r theta phi, these two things are given to you, will be given to you in the examination. Like this time you would have seen, they would be given to you in a table of formulae, the cheat sheet, where you can find them, so you don't have to memorize them. But at least I hope you have gained enough conceptual clarity into how to solve all of these variations. Only on one variable. Once again, I'm stressing. Otherwise, there is somebody might take it into his head to solve for Laplace's equation as V depends on S, phi, and Z, all three variables simultaneously. That will be as I said, a considerable mathematical challenge, but not really needed for our present purposes. Okay, so the last thing that is left to take up now in the cylindrical coordinate system is the variation along the S direction. Let us see. So, I'm sorry, just a minute. One thing that, once again, I'd like to stress is that we have solved for the Z variable and the phi variable going from back to front, Z, phi, and S. There is a reason why I'm going from back to front, because Z is fresh in our mind, like we have discussed in the Cartesian system, so that's why. And we have seen that X, Y, Z in the Cartesian system will give you three straight line solutions, each of them depending on X, Y, and Z. In the cylindrical system, once again, we have found that both Z here and phi here give the solution of the straight line. Now we are about to investigate the variable S, the variation of the function V, the potential function V on the variable S, coordinate S. Let us see. No phi or Z dependence. Variation is only along the S direction, and you have got two concentric cylinders. So I hope you are able to understand how, get the geometrical idea very clear. When you are talking about the Z variation, the two boundaries are the bottom disk and the top disk. Okay. Both are flat surfaces, by the way, but they have a circular edge, circular periphery. When you talk about the variation of the phi variable, you are talking about a door, as in the door of your room. This door is shut. This here is opened up by an angle alpha. Okay. The surface is still flat, and the periphery is like a rectangle, as opposed to the previous case where the periphery was a circle, a circular circumference that you have. But here it's like a rectangle. And now we are talking about cylindrical surface. This is the first surface. This inner cylinder is the first surface, and this outer cylinder is the second surface. So these are the two boundaries. The surface is no longer flat. The surface is along the curved barrel face of the cylinder. So you're talking about two concentric cylinders. You take Laplace's equation, d2v is equal to del 2v is equal to 0, as in this case. But now, since you just have a variation only upon s and not on phi and z, so v does not depend on phi, therefore this will be equal to 0. V does not depend on z, therefore this will be equal to 0. You'll be left with only this, 1 by s dds of s dv ds. 1 by s dds of s dv ds is equal to 0. Del 2v is equal to 0. Hereafter, now we will get into some mathematical complication. I ask you to be quite attentive to this discussion. Let us see what we can do. First, 1 upon s dds of s dv ds is equal to 0. 1 by s is in general not equal to 0. But if this into this dds of this whatever is equal to 0, then it means that dds of s dv ds is equal to 0. Okay. Therefore, s dv ds must be a constant quantity. S dv ds is equal to A. Capital A is a constant quantity. Okay. Therefore, so basically we have carried out done three things in 2 lines. First step is writing always in all of these Laplace problems, the flow is del 2v is equal to 0. Then as per your problem, you write the appropriate operator, 1 by s dds of s dv ds is equal to 0. That's the second step. Then you carry out the first integral, which this is the first integral. That's the third step. And the first integral is s dv ds is equal to A. Therefore, dv ds is equal to A by s. Okay, fine. Now you'll have to find the second integral. This is the second integral. V is equal to A ds by s integrated. So 1 upon s. When you integrate it, it will give you log s. No longer a straight line. You've got a logarithmic dependence now. A log s plus b. Okay, so that is what you have. Now you shall apply the two boundary conditions as has been written over here. What are the two boundary conditions? The inner cylinder has got a radius A. S is equal to A. The outer cylinder has got a radius S is equal to B. And the potential on the inner cylinder is V is equal to 0, and the potential on the outer cylinder is V is equal to V naught. Incidentally, one thing I would like to stress, let me get back to a few points. One thing I should like to mention over here is that you would have noticed that always I'm writing V is equal to 0 at one boundary. V is equal to 0 here. Then again, I have written V is equal to 0 here in the cylindrical Z variation and the phi variation problems. Then here also, I have written V is equal to 0. And at the other end, I've written V is equal to V naught. You may very well ask me, why are you just writing 0 at one boundary? Why not, V is equal to some non-zero value? And then at the other end, also some non-zero value. I will say it doesn't make much of a difference because ultimately, what matters is the potential difference. So suppose I had written V is equal to, let us say, A over here. Then this thing would straight away have been equal to V is equal to V naught plus A. But that A by itself, A, B, C, whatever, V is equal to C, let us say, we have already used A and B here. So V is equal to C here. and then this value would have immediately been equal to V naught plus C. But you'll always notice that you can assign any quantity or any value at a potential, but a potential is always correct within an arbitrary additive constant. What do I mean by additive constant? A constant that you add, such as this thing, plus B. This is an additive constant, whereas A into Z, I'm multiplying A with Z. So A is a multiplicative constant, whereas B is an additive constant. You multiply Z with A, therefore A is a multiplicative constant and B is an additive constant. You add a constant. So what I mean is that a potential is correct only to within an arbitrary additive constant. Just now I explained to you what an additive constant is. An arbitrary means that it can have any value. You really don't know. But then it doesn't matter whether you know it or not, because ultimately what matters is that the measurable quantity is always the potential difference and not the potential in itself. So if I write V is equal to C here, then the upper value would immediately be V naught plus C. So that C will always be there. So but it will make our mathematical task difficult. We are not going to lose anything physics-wise if I just say that let's set the value of C to be equal to 0, and so that will make our task much easier as we get along. So this is just like, basically, in mathematical terms, what I've just done is a shifting of the origin of coordinates, if you like, within that constant C. As a result, your solution will always be like V is equal to A into Z. So here, V is equal to A into Z. Okay, so here also we have just done the same thing. V is equal to 0 at one boundary and V is equal to V naught at the other boundary. Let us now apply the same principle here. We were discussing the cylindrical coordinate system. V is equal to 0 and V is equal to V naught. S is equal to A and S is equal to B respectively, where B is the outer radius, larger radius, B is greater than A, small b and small a. And you also have two constants over here, large A and large B, or capital A and capital B. Okay, let us see now. When S is equal to A, small a that is, V is equal to 0. Okay, you notice one thing. I did not set, as in the previous problems where we wrote phi is equal to 0 or Z is equal to 0. Those were the boundaries we chose in the previous problems. Here, I have not chosen S is equal to 0 as one boundary. Why have I not? Because you'll have a huge deal of trouble if S were to be equal to 0. Just see log of 0. Log of 0, thereafter there's no point worrying about all the other constant and all those things. Because if you put log of 0, immediately V will be equal to minus infinity. Log of S, log of 0 is minus infinity. So basically, these boundary conditions should be well designed, well defined, and well behaved. Well behaved boundary conditions, as we say in mathematical terms. You don't just choose a boundary condition that will give you a heap of trouble. So yeah. So S is equal to small a and V is equal to 0. That is what you write. So if 0 is equal to capital A into log of small a plus B, therefore B is equal to minus capital A log of small a. Therefore, V is equal to, now you follow this thing, capital A, what is V? V, therefore, if B is equal to this thing over here, minus capital A log of small a, then capital V will be equal to capital A log S minus capital A log small a. Put the two things together, log of any two numbers, log X minus log Y will be equal to log of X by Y. So that's the principle that we have applied over here. V is equal to A log S by A. Okay, now we shall apply the second boundary condition, because what is the purpose of using the boundary conditions? These two constants, capital A and capital B, in all of these problems are arbitrary constants. B in this case is an arbitrary additive constant. A in our cases is an arbitrary multiplicative constant. So you have to be incidentally quite careful in how you choose your boundary condition. Otherwise, if your constant values become something wrong, or something undesired, not desired, and your problem will go completely off. I mean, your solution will go completely off. Okay, so when S is equal to B, in this equation, we shall put this. So first we have fixed the value of capital B. Now we just have got one unknown constant, unknown arbitrary constant, which is capital A. So this is just algebra, nothing else, what we are doing. S is equal to B, we put over here. V is equal to V naught, we put over here. That's the second boundary condition. Therefore, capital A will be equal to V naught divided by log of small b by small a. Okay, thereafter, we shall have to put this value here. So V is, this value we shall put here. V is equal to V naught divided by log of small b by small a into log of S by A. And after that, you can just work on this thing. Is equal to V naught if you want to expand it, log of S minus log of A divided by log of B minus log of A, if you like. And what about the electric field? The electric field is, let us see, gradient of V is equal to del V del S S cap. V does not depend on S, as in our current problem. V depends only on, V does not depend on phi and Z, it depends only on S. So del V del phi will be 0, del V del Z will be equal to 0. You're just left with this thing, and E is the negative gradient of the scalar function. So it will be minus del V del S S cap. So E will be minus dV ds S cap, because we are dealing with a one variable problem. So dV ds S cap. And so what is dV ds? Let us see now. dV ds is equal to A by S. And what is A? The value of A we have just found. So we shall just put over here minus V naught by log of B by A into 1 by S, S cap. That is the electric field. So you can see, step by step, basically that is always the flow you maintain. First thing you write in solving Laplace's equation is del 2V is equal to 0. Laplacian operator of V on V is equal to 0. Then you write this specific operator as per your problem. Then first integral, then second integral. Thereafter, so 4 steps done. 5th step is to apply boundary conditions to fix the 2 arbitrary constants, A and B. And the 6th step is to write the electric field. So this is a very simple way to find the electric field. I have stressed this point once earlier also, that why, if ultimately we are not even interested too much in the potential. We are interested in the electric field, electric vector field. So Laplace's equation, or the potential formalism approach, gives us a very useful way of finding the electric field without having to worry about the direction. First, you solve for the scalar potential. As soon as you get the scalar potential, then the second thing that you do is to write E as the negative gradient of the scalar potential. And solve for the value of E. So here, that way, it's more simple. Of course, I have also mentioned to you there's a price to be paid. And what is the price to be paid? That you shall have to work with a second order differential equation. What do I mean by a second order differential equation? It means that you shall have to do 2 integrations. When you're doing 2 integrations, it basically means that you are working with a second order differential equation, and each integration step will introduce an arbitrary constant. You have introduced 2 arbitrary constants over here, capital A and capital B. However, that said, one last thing to touch upon now is that this is one case where V does not come out as the solution of a straight line. V is not A into S. V is A into log of S. So out of the 6 variables we have worked with so far, namely X, Y, Z, or 6 variables we have considered so far, we did not work with X and Y, but we just said that whatever we have done with the Z variable in Cartesian coordinates will be the same as what we can do with the X and Y variables in the Cartesian coordinates. So X, Y, Z, all 3 of them yielded the solution of a straight line. In cylindrical coordinate system, Z and phi also yielded the solution of a straight line, but S has not. S has given you a function that is like a logarithm. So please bear that in mind. Okay. Now we shall go to the third coordinate system, spherical polar coordinates. This is by far the most difficult one. The most difficult will be the theta variable, as we shall see. So Laplace's equation in spherical polar coordinates. Let us see. Our first task, as always, as per the algorithmic flow I have mentioned to you, will be writing the Laplace equation in full. Del to V is equal to 0. Okay. We are dealing with the polar coordinate system, and in the polar coordinate system, just to get a little ahead here, I have written the operator for the theta system. The theta one is the most difficult. That's why I had to. So here you have been given. So this is the Laplace operator in full using the spherical polar system, the r theta phi system. Here you are. This is the first operator, this is the second operator as it depends on theta, and this is the third operator as it depends on phi. When we deal with a potential function that depends only on the variable r and not on theta and phi, then d theta will be 0, d2v, d phi squared will also be equal to 0, and you'll just be left with 1 upon r squared, ddr of r squared, dv dr. That is what we have kept over here. 1 upon r squared ddr of r squared dv dr is equal to 0. This is something we discussed also in one of the previous cases. And in fact, this is the most important case in the spherical polar system, because we shall be working with electrostatic fields, and electrostatic fields have only the radial dependence, not the theta and phi dependence. And so if you want to solve Laplace's equation for an static distribution of charges, this is the operator that you shall have to use. 1 upon r squared ddr of r squared dv dr is equal to 0. Okay, fine. 1 upon r squared into this quantity is equal to 0. But 1 upon r squared is not equal to 0 in general, unless r goes to infinity, but that's not what happens all the time. So it basically means then that ddr of r squared dv dr is equal to 0. Okay. If that be so, then it simply means that r squared dv dr is a constant quantity, capital A. Okay. We have done the first integral. This is the first integral. Like I said, step by step, write Laplace's equation, recast the equation in the appropriate operator as per your problem, carry out the first integral, and the first integral is r squared dv dr is equal to a constant quantity. Therefore, dv dr is equal to a to 1 upon r squared. Okay. Next is the second integral. Remember the flow. We have done the third step. We are now on the fourth step. Second integral is dv dr is equal to a by r squared. When we integrate that thing, it is v will be equal to minus a by r plus b. I hope you have no difficulty. R raised to minus 2 dr integrated will give you r raised to minus 1 divided by minus 1. Okay, so that divided by minus 1 comes up here, and r raised to minus 1 is 1 upon r. So this is the second integral. B is equal to minus a by r plus b, the second integration constant. As soon as you see an arbitrary constant appearing, you immediately know an integration has been carried out. Although I have not explicitly written integrals, but they are quite trivial integrals really. So a and b are two arbitrary integral constants. Next task is to fix the arbitrary integral constants with the help of the boundary conditions. Let us see how. Let's go back to the diagram. We choose an inner radius, two concentric spheres. What are the two boundaries? The boundaries of the problem are an inner spherical surface and an outer spherical surfaces, and both spherical surfaces have the same center, two concentric spherical surfaces. R is equal to small a, R is equal to small b. At the smaller spherical surface, V is equal to 0, the potential, and at the outer surface, V is equal to V naught. Those are the two boundary conditions. So when V is equal to 0, at R is equal to small a, you write 0 on the left-hand side is equal to minus capital A by small a plus b. Therefore, capital B must be equal to capital A by small a. You have fixed one arbitrary constant with the help of one boundary condition. That is why you need two boundary conditions, because you have got two unknown constants. And for two unknown constants, you'll need two independent conditions, mathematical conditions. Each of these two boundary conditions gives you your required independent condition. So V, capital V is equal to capital A by small a minus capital A by R. That is what you have. When R is equal to B, small b, V is equal to V naught. Okay. Therefore, V naught is equal to a little bit of school level algebra, LCM and all that. AB to B minus A. Therefore, capital A will be V naught into AB by B minus A. So now you will put, so here's your final solution. V is equal to V naught into AB by B minus A. This thing is A into 1 by A minus 1 upon R. If you look at the right-hand side, only this R here is the independent variable. Everything else is a constant quantity given in terms of the boundary conditions. And what are the values that come out from the boundary conditions? A, B, and V naught. Small a, small b, and V naught. And that is what you have. Small a, small b, and V naught. All of them you have here. So there you have all of these things. Next task is for you to write E is the negative gradient of a scalar function. And what is the scalar function that you have over here is minus dVdr is equal to r cap. When V does not depend on theta and phi, that is the gradient of V. So that is what you have, and you've already got dVdr here. What is dVdr? A by r squared. And so you write so dVdr is equal to, and A is equal to V naught AB by B minus A. So minus V naught AB by B minus A by r squared r cap. Do you realize something? I've written something over here. We are talking Laplace's equation as it should be for a static charge distribution. If you have a distribution of static charges and you're standing far away from the charges, then Gauss's principle, Gauss's law of electrostatics will tell you that to you it should look like that all the charges were concentrated at the center, at one point at the center, and it will look like a point charge. And the electric field due to that point charge would look like what? As it would be given by the Coulomb law. And what is it? Q divided by 4 pi epsilon naught by r squared r cap. The same thing you see over here. For the greater part of it, all the major things are here. R cap is there, 1 upon r squared is there. This is the constant quantity, which in the Coulomb formulation should be Q divided by 4 pi epsilon naught. But you have taken a different approach to come to the same thing. You just get the same thing essentially. E goes off as 1 upon r squared r cap for a point charge. I mentioned to you something else also. Let us see. When we solved all the Gauss problems, I told you that for a point charge, the electric field, just a minute. For a point charge, the electric field falls off as 1 upon r squared, r cap. For a line of charges, as in a cylindrical system, this is a cylindrical system. You see that? You have charge, electric field, an electric field is traveling through this charge-free region. The charges are somewhere here within the first boundary, but I've just asked you to study the system within the two boundaries where there is no charge. But the source is in a cylindrical configuration, therefore the electric field will fall off as 1 upon S. It's just the same thing you're getting over here. E goes as 1 by minus V naught by log B by small b by A, some constant quantity into 1 upon S, S cap. I hope you realize that fact. And then what did I tell you about a plane full of charges? For a plane full of charges, E does not change at all. It's a constant quantity everywhere. If you go from pages, I'll upload those notes shortly. If you go in along for all the Gauss problems, you will make this little interesting discovery. And consistently, the variation, the functional dependence is being upheld through a very different approach, not the Gauss kind of an approach, but the Laplace Poisson kind of an approach. And so there you also see the same feature. If you have plane symmetry, electric field will not change. If you have cylindrical symmetry, then along the S direction, electric field will go as 1 by S cap. And if you have spherical geometry, the electric field will fall off as 1 by R squared, R cap, times some constant. So they all are self-consistent, consistent with each other. Gauss and Laplace, both of them are consistent with each other. Okay, let us now take up the theta variation. This is going to be a very long discussion. We should not be able to finish it today in the 9 minutes that is available to us still for this lecture, but I shall start the discussion. First, you be a little careful about understanding the geometry. That is what it is. V depends on theta only, dependence only on theta. V depends only on theta. R and phi will be arbitrary. We don't know what they are. Let us see. If V depends only on theta, first let us look at the mathematical part of it. V does not depend on R, therefore this will be 0. V does not depend on phi, therefore this will also be equal to 0. If V depends only on theta, then only this part will be non-zero, and that is what you write. 1 by R squared sine theta, dd theta, sine theta, dv d theta. This is dv d theta, as I've written in clearer handwriting over here, is equal to 0. This is the operator that you shall have to work with. Okay, so that is one side of the story. Let us now look at the boundaries. The first boundary is at theta equal to theta 1. We are dealing with the polar coordinates. X, Y, Z are the three polar axes. Theta is equal to 0 when you are on the Z axis, and then theta has got an increasing direction. You're coming down and going this way. So here at the angle theta equal to theta 1, V is equal to V naught. Here at the angle theta is equal to theta 2, V is equal to 0. You notice that this thing, this theta, could be anywhere on the conical surface of an inverted cone or a funnel. In chemistry laboratory, I believe you would have worked with a funnel. So chemistry laboratory as in your school, class 11 and 12. So there you have a funnel-like structure. Theta is the same everywhere. Then you flatten the funnel a little, your theta increases. To increase theta, you have to flatten the funnel. So this is another flattened funnel. A funnel is also something with which you pour oil from a large tin into a small container or something like that. So there you have the second funnel. So theta is, so when you fix the value of theta, you're anywhere on the surface, anywhere on the rim of this inverted cone. So you have got these two boundary conditions. What is your task? How is the field varying between this conical surface and this more flat conical surface? These are the two boundary surfaces. You are in that sort of a wedge-like area within these two surfaces. So that's the area of your volume of space of your interest. Okay. And when you take this operator, as I mentioned to you, you're dealing only with the theta variation. Del V, del R, and del V, del phi will go away, and you are just left with this thing. 1 by R squared sine theta, dd theta of sine theta, dv d theta is equal to 0. 1 by R squared sine theta in general is not equal to 0, unless, of course, I mean, 1 by sine theta can never be equal to 0, because it means that sine theta must go to infinity. That doesn't happen. Sine theta always varies between +1 and -1. Only when r goes to infinity, you can have that possibility, but we are talking about any finite value of r. Therefore, 1 by r squared sine theta is not equal to 0. But that thing multiplied by this quantity is equal to 0, which means that d d theta of sine theta dv d theta is equal to 0. If d d theta of this quantity is equal to 0, first integral we are solving, sine theta dv d theta is equal to a. An arbitrary integral constant has been introduced. We have carried out the first integral. Now we shall have to be a little attentive. As I said, this is the most difficult of all the 9 cases we shall take up. 9 cases as in x, y, z, 3 cases in Cartesian, s, phi, z, 3 cases in cylindrical, 3 and 3, 6, r, theta, phi, 3 cases in spherical. We have already discussed r. That was the 7th case. This is the second last, the 8th case that we are taking up. So dv d theta is equal to a divided by sine theta. And what is 1 by sine theta? Cosec theta. A into cosec theta. So this integration is not a very easy one. So that's why so v will be equal. We are now going to work out the second integral. V is equal to a integral cosec theta d theta. Okay, I just refer to the table of integrals. Integral of cosec theta d theta is log of tan theta by 2. You can work it out by yourselves. Not a very 1 by sine theta. You can then break it up, or sine theta is equal to whatever all that cos theta. You have to apply that formula. What is it? Sine 2 theta is equal to 2 cos theta, whatever, all that thing. You can work it out, but I've just referred to the table of integrals. Here you are. Log of tan theta by 2. Okay. So V is equal to A integral cosec theta, this thing, A log of tan theta by 2 plus second integration constant. We have carried out the two arbitrary, integrals. And in the process, we have introduced two arbitrary integral constants, A and B. So when theta is equal to theta 2, V is equal to 0. That is to say, we are applying the second boundary condition first. Theta is equal to theta 2, V is equal to 0. So V is equal to 0 over here. A is this minus, 0 is equal to A log tan theta 2 by 2 plus B. Therefore, B, capital B is equal to minus capital A log tan theta 2 by 2. Hence, capital V is equal to A log tan theta by 2 plus B, where B we are writing like this, minus capital A log tan theta 2 by 2. Okay. So now we have to worry about only one integration constant, capital A. So when theta is equal to theta 1, V is equal to V naught. As I said, we have gone through the hereafter, there's no physics really. We are just doing a whole lot of differential calculus problems. Solving a lot of calculus problems. So theta is equal to theta 1, V is equal to V naught. Let us see. We have V naught here, capital A, log tan theta 1 by 2, minus, taking A as a common factor. So A here, minus, we have put a square bracket, minus log tan theta 2 by 2. Okay. With that, now take capital A as a common factor. Capital A is equal to V naught divided by log of this minus log of this, which we are writing as log of this divided by this. Capital A is equal to log V naught divided by log tan theta 1 by 2 divided by tan theta 2 by 2. Hence, capital V will be equal to capital V we have just seen is equal to A log tan theta 2 by 2 minus tan theta by 2 minus capital A log tan theta 2 by 2. And so V is equal to capital A log tan theta 2 theta by 2 divided by tan theta 2 by 2. We are using this formula. V is equal to taking a common log of this by this. That is how we are writing log of tan theta by 2 divided by tan theta 2 by 2. That is into capital A. And then we are substituting for for capital A, which comes from here. And so V is equal to V naught log tan theta 1 by 2 divided by tan theta 2 by 2. Just give me a minute. I should be able to finish this thing. Into log tan theta by 2 divided by tan theta 2 by 2. Okay, with that, once we have this thing, we have got the potential function. E is the negative gradient of the potential function. As you can see, we are dealing with V as it depends only on theta, not on R, not on phi. So this will vanish and this will vanish, and we will just be left with this minus 1 upon R dv d theta, theta cap, and dv d theta. Just a while ago, we solved for that. dv d theta is equal to A cosec theta. And so that is what we have, minus A cosec theta by R, cosec theta, theta cap. And so E is equal to minus 1 upon R. And then capital A, we are substituting. Capital A is substituted by this thing, V naught divided by log tan theta 1 by 2 divided by tan theta 2 by 2. V naught by log tan theta 1 by 2 divided by tan theta 2 by 2 into cosec theta, we are writing as 1 by sine theta, theta cap. Anyway, this is the end of the theta variation discussion. I have been able to finish it by taking an extra minute. In the next class, we shall talk about the dependence on phi, but the next class will not be held on Friday. Friday is a holiday on account of Vijayadashami, so we shall meet next week. However, just I'm stopping the sharing now. However, this afternoon, do not forget that we have a tutorial. We shall meet for the tutorial, and I shall discuss the pending